the main thing to recap from last time is just that we had continued talking about electric forces, and that for point charges, meaning just little globs of charge that are concentrated into little balls, the force between them is given by Coulomb's law. Just depends on the size of the charges and the distance between them. And we found that if we've got multiple charges that we want to find what they do to some particular charge, so in this case we looked at charge 1 and said what do charge 2 and 3 do to it, we use vector addition. So we find the forces as usual using Coulomb's law, but then we have to add them as vectors, and that will give us the net force. So we are going to pivot perspectives a little bit and talk about something that is related to electric forces but is different. And this is typically the hardest thing for people to wrap their heads around in Physics 2, period. Electric fields, because they're sort of an abstract thing. So the motivating question for why we would ask about them is, well, for Physics 1, we always talked about things like friction and tension, where stuff's touching. One thing's rubbing on another, or you've got a rope pulling on something, or for a normal force, something's in contact with something else. For this, for charges, it feels different because they can be pretty far away from each other and still exert forces. How is that possible? And the solution that physicists have come up with is to say they're not really just separate from each other. There is something connecting the space between them, and we call that the electric field that each object creates. So instead of thinking of forces as one thing is a distance away from another and just magic happens, start thinking of it as one object is sitting in an electric field created by the other. It's an invisible ocean around the object that other objects interact with. And if you think of it that way, it still becomes one thing touching another. It's just something we can't see, the electric field. So to get that idea across, I'm going to call the electric field an aura, which I don't really like that word, to be honest, but it sort of gets the idea across of an invisible thing surrounding every charged object. That extends throughout space. And the reason it's such a difficult concept to get your head around is that we can't see them. I can't point to an electric field and say, look, there it is. You know about that thing, because we can't see them. All we can do is see what they do to charges. And so our best measurement tool to look at electric fields is a charge. We call it a test charge. It's really more of a thought construct or a thought experiment. You imagine pulling out a little charge near some other charged object and say, what's going to happen to it? And we call that a test charge. It's a tiny positive charge, and positive is important. We're always going to assume it's positive because we'd get different answers for everything if we pulled out a negative charge to test stuff. It's a tiny positive charge used to measure the strength of another charged object's electric field. And so to motivate this, gravity has a similar issue. How is it that the Earth pulls on the moon and keeps it in orbit when it's so many miles away? Well, we come up with the idea that really they're not just totally distinct objects. The moon is sitting in the Earth's gravitational field, this invisible thing surrounding the Earth, and that's what the moon is actually interacting with directly. And so we're going to use this as an analogy to try and understand how we think about electric fields. So say you come to some distant planet which you don't know a lot about, and we'll say it has some mass, capital M. Your goal is to measure the gravitational effect this planet has on other objects. So you get out of your spaceship. What is one simple thing you could do to start thinking about the gravitational effect this planet has? See something in. Yeah, drop something. Perfect. So I could just pick a rock up off the ground at some point, and I'm gonna give that rock the mass m0 is what I'll call it. And that's gonna be what I call my test mass. How will I know? How will I be able to tell the difference between a planet that has very strong gravity and one that has very weak gravity?
Fast that the rock drops to the
Yeah.
ground.
Yeah, and so I'm actually measuring the acceleration of the rock. How much speed does it gain per second? And even slightly more directly, what I could do is look at the force on the rock, put it on a scale or something like that, and say, well, how hard is it being pulled at that point? So I'm going to measure the force on that test mass. The only problem is the answer I get if I just measure the force is going to depend on which rock I picked up, right? Because a more massive rock is going to feel a stronger pull. It's going to weigh more than a less massive rock. I have a problem. If I'm using a rock to test this, the size of that gravitational force is going to depend on which rock I used. How can I come up with a number that does not depend on which rock I dropped?
Did you just use the same rock?
Well, sure, but if the goal is to describe the planet, do you really have to make sure anyone who comes to this planet has my special rock? It really shouldn't depend on what I use to measure this thing. So I have to come up with a way to get a measurement that doesn't depend on the particular rock that I picked up. That's the issue.
You could test several rocks and find an average.
That's starting to get at the idea I'm looking for. So let's look at something kind of concrete. Say I picked up a rock that had twice the mass of this one. What would happen to the force of gravity on that rock? How much larger would it be?
Twice as strong.
Twice as strong. So gravity would pull twice as hard on that rock. But doesn't that mean if I take that force that I measured on my particular rock and divide by the mass, I'm going to get the same answer for either of those two rocks? Because if one is feeling twice the force and it has twice the mass, that cancels out, right? Okay, so that's what we're going to do. This will be my measurement for the effect of the planet itself. Reason I know it's the planet itself is the number I get from this will be the same no matter which rock I used. So it must be a property of the other thing in this interaction, the planet. And so I will call this the gravitational field. That's my definition for the gravitational field. And so all I have to do is just keep going around to different points. And even if I used some other rock, say it does have a much bigger mass, twice m0, that's perfectly fine. Yes, it will feel twice the force, which actually, you know what? I think I want to use black for this because I want to save red for the field. I'm sorry, I'm jumping colors. So yes, that bigger rock will feel twice the force, but if I divide that force by the mass of the rock I used, I will get something that didn't change. It will be the same number. This field, which I know that's kind of hard to see, but this field, it'll read the same no matter which rock I use. And it should. It's a property of the planet, the big mass. And so to characterize gravity on this planet, all I do is I just keep walking around to different points. And I keep dropping this rock. And dividing the force that it feels by the size of the rock I'm using. And I'll start to get this description of the gravitational field. If I go up a little bit higher, go up on a ladder, maybe I'll find that the rock doesn't feel quite as large of a force because I am farther away from the planet. And now that actually is saying something about the planet itself, I am farther away from it, the same rock that I was using from before is going to feel a smaller force. And so the field is actually weaker at this location. And as I get farther and farther away from the planet, I will see the field get weaker and weaker and weaker.
I have a question.
Yes.
So the reason why like you're going farther away and it's when you drop the rock, its acceleration is decreases because of the gravitational field.
Yes, it is getting weaker. And even if that sounds abstract, look at what I'm calling the field, what I've chosen to define it as. If I get farther away from this planet, I am expecting that force to get smaller, even though the mass did not get smaller. So the ratio of them will get smaller and smaller.
Is that why if you were to go to the moon, you will feel the gravity it's much weaker than it is on Earth.
Yes, but that is still intrinsic to the planet itself. So it's not just about distance in that case, it's because the moon itself has less mass than the Earth.
Okay,
It
thank you.
creates a weaker field around it. Yes. And so at this point, you might be wondering, okay, but what really is this field? What does it represent about this planet? And I can give you an answer for gravity. For the electric field, we don't have something as simple as this just yet. But we know how to find the force of gravity on an object. All we do is we take its mass and multiply by g. On Earth, g is 9.8. Something gains 9.8 meters per second of speed each second that it falls. On the moon, g is 1.6. On Jupiter, it's 19 point something, I think. But what we're going to do is that is the numerator. I'm dividing by the mass of the rock I used. And so we see that it truly does cancel out. This measurement I'm taking does not in any way depend on which rock I used to take the measurement. It is actually about this value g, which is a property of the planet, not a property of the rock. So gravitational field is actually just, what is g? What is the acceleration of objects on your planet? And that number is different for different planets. Okay, so that's the idea. The field is created by the planet's mass. So big M. We can use a rock, a test mass, which we called M0, to measure G, but G does not depend on which rock we use. It shouldn't. We're trying to figure out something about the planet. The rock is just a measurement device. And then you might ask, well, why is this useful to do? Well, now I know what's going to happen for anything on that planet, my own body even. I can figure out how strong a force I will feel, because all I have to do is take that measurement of g and multiply by my mass instead of the rock's mass. So g is something that is totally descriptive of the planet, and once I've cataloged it once, I'm done. I can figure out the force on any object I want that is near that planet. That's the utility of this. I don't have to redo these measurements every time I want to find forces. Well, now I'm going to pivot over to some unknown charge. We'll use a big Q. So I have the same question. I want to characterize something about this charge. I cannot see the field it creates around it, but I know there is something around it because when I hold a charge up next to it, something happens to it. So if I have a little charge, I will call this my test charge. If it's a little positive charge, what will the big charge do to it?
Repel.
It'll repel it in this case. It's pretty far away, so it may not feel that strong of a force, but it will feel some amount of force. If I hold it a little bit closer, it will still be repelled, but it may be a larger force because it is closer. So this is still just a little tiny charge I pulled out of my pocket, a little tiny positive charge. But I have the same issue. If I'm trying to characterize something about that big charge in the middle, I should not get an answer that in any way depends on what little charge, what Q0 I pulled out of my pocket to measure. So the force is going to depend on that. If I pull out a bigger charge out of my pocket, it's going to feel a stronger force. So I need to invent a quantity that doesn't change, no matter which sized charge I pulled out of my pocket to test this field. How do you think I do that?
F on Q naught over Q naught.
Yep. Because if I pull out something with twice the charge, it will feel twice as strong a force. But it also has twice the charge. And so that ratio, even if both things are twice as large, it stays the same. And therefore, it is not a property of the little test charge, it's a property of the big charge. Sometimes you see absolute values thrown in here. It doesn't matter because it's a positive charge, but sometimes you see that. Okay? And we're going to give this the special name E, capital E. So it's not as familiar as G from Physics 1, but it serves the same role. And that's the idea. So E, the field, is created by the big charge. Q. We can use a test charge Q0 to measure this electric field. But the electric field does not depend on what test charge we use. To give another analogy here, imagine that you had a thermometer, and when you pulled that thermometer out, it changed the temperature of the room. It was like a space heater. It was just a really warm thermometer. Well, for one, I'm not sure how you would measure temperature with that in the first place, but say you could. Would you feel like that's a reliable measurement of the room's temperature?
No.
No, because it is changing something about the room. Same deal here. We should not expect our measurement device to in any way affect a measurement about the space, about the room that we're in. So, it better not depend on the size of the test charge. It better not depend on the size of the rock we dropped, or else it is a bad measurement tool. And that is why we divide out by it. And we can continue this procedure at lots of different points around our big charge. Maybe here it feels a certain force, and then here, and here. But what I'm ultimately interested in, which, I think I did it again. I wish I had labeled these in black, because that's analogous to the other picture. What I'm ultimately interested in is actually what I get when I take that force and divide by the size of the test charge I used. And it is something that is strictly a property of the big charge. It's the thing I truly want to know about. The aura that big charge has in the space around it. So that is our definition of the electric field, is we pull out any little charge we want, we measure the force on it, but then, to get something that does not depend on what particular charge I use to measure this field, I divide out by it. So this is the field of the big charge, the one I called Q. But we measured it with the little charge. The test charge, Q0. And that's what you're seeing on the right side. This procedure I go through is I pull out my little test charge, I measure the force on it, and then I divide by that to get something that is actually a property of the thing I'm measuring. In this case, it's this PVC pipe. And you notice in this second picture, the test charge doesn't appear because I'm done using it. It was just a tool to measure the temperature of this space, the electric field around this PVC pipe. You don't need your thermometer once you know the temperature in the room. It's just a device. You need it to get there. So same here. The electric field is actually due to this thing. I just used a test charge to figure out what it was. All right, I really spent a lot of time on it because it is the thing that is the sticking point in this class. If electric fields don't make sense, the whole next month is not going to make a whole lot of sense. So they really do need to be something that you understand comfortably. All right, and now we ask that new question of, well, what if something else comes along, some other person, or they bring their own rock that they want to find the force on, or they have a spaceship and they say, hey, what's the force on this going to be? Well, they don't have to do this. I just did the hard job. Now that I've determined the field at every point around this big charge, if I bring some new little thing along and I want to say, well, how hard is it going to be pushed or pulled by that big charge? Well, all I got to do, so I'm going to use new for this label. All I got to do is take that field that I already measured and multiply by my new charge that I brought. And that will tell me this new force. So this is a third charge I'm bringing into the mix. I started with a big charge. I brought a little tiny test charge up close to it. I measure the force on that, and I use that as a means to figure out. So this is like later in the day. I now know at this location in space that the electric field is some number and has this particular direction. And if some guy brings along his new charge and places it right there where I measured that electric field, I instantly can figure out what the force on it will be. I don't have to measure anything. I can calculate it now and find that it is the size of that charge that he brought times the electric field strength at that location. And that's the thing at the end of the previous chapter where I was like, say I swapped out the charge for a different one, do the problem over again. It would be terrible to have to do that, but with the electric field, we don't need to. Once we've calculated the electric field once, which it is painful that first time, but once you've done it once, you never need to do it again. You can figure out the force on any charge you place there. All right, so let's see if this idea kind of makes sense. I have measured an electric field in this region of space. Maybe it was from some big positive charge over here. I don't know. Because now that I've measured it, it is actually the important thing to worry about, the electric field itself. You know what, just for illustration's sake, I'll put the big charge there. So if I found that the electric field points this way, what that actually is saying is I put a little test charge there earlier on, I measured the force on it, and I found the force on that little test charge to be this way. When I divide by the size of the test charge I used, I get this quantity E, and it is describing something about the big charge. Now I bring my new charge along. If it's a positive charge, which direction will it feel a force when I place it in this electric field?
To the right.
To the right. The same as the test charge because they are both positive. So the direction of that force will be along the electric field if I bring a positive charge with me and dip it into the field, see what happens to it. If it is a negative charge, what will happen?
Go to the left.
Yeah, so now me or some other guy brought along his negative charge, and he said, all right, what's the force on this? I say, oh, you brought a negative one. Well, it's going to be opposite the field that I measured. And notice, nothing else has changed. I did not do anything different with what's creating this field. It's still some big positive charge over here, let's say. I still measured the force on my test charge to be to the right as well. That's how I determined the direction for these red electric field vectors. What's different is the charge I brought to dip into the field now, this blue charge. So there's kind of 3 charges we're discussing here. And this blue one, it will feel a force opposite the electric field if it's negative. All right, that's separately a statement about the magnitude of the force and the direction. We broke it into 2 separate steps. And that's generally what I'm going to recommend doing to think about this. This is the better way to think about it for solving problems, is in 2 steps, the size of the force and the direction of it, if you know the field. But you could, if you wanted to, write it as a single equation that accounts for magnitude and direction at the same time. But I don't recommend using this much. It's going to be better for me. It's going to be better for derivations, because then I don't have to separately think about size and direction when I'm deriving something. So you'll see this pop up occasionally, but when we're thinking about stuff, splitting it into parts is going to be better. But what you do is just know absolute value on the charge. Why does that work? Because say Q is a positive charge. This is my Q nu that I'm talking about. Say it's a positive charge. How do the force and electric field vectors compare to each other?
Same.
Yeah, so we're looking at this case. But the math works out because for vectors, a positive means don't flip it over, whereas a negative means do flip the vector over. So if Q nu is positive, F is a long E. If it is negative, F is, well, we take the electric field vector, we scale it by the size of this charge, and then we flip it because it is a negative charge. So it is opposite the electric field. So all that's baked into the math if we write it this way. The previous way, we had to separately think about how big is the force and what direction is it. But I like that better because I think it's less confusing, to be honest. So now we are going to act as what I call the electric field inspector. You're the guy who has to find the electric field the first time, unfortunately, but it's for the benefit of everyone else who brings a charge along and asks, what's the force on this thing? So what you do is you get called to a job site where they say, hey, what's the electric field here at this point in space? And you say, oh, okay, no problem. I'm going to pull out my trusty test charge out of my pocket, and I'm going to measure the force on it. So that's what I've got right here. My force on my little test charge. How do I determine the electric field at this point in space?
Divide the force by the charge.
Yep. And that's great because if I accidentally brought my other test charge, maybe it's worse than this one, it's twice as big, it's heavier to carry around, I'll still get the same answer because that other test charge would feel twice the force as well. The ratio of these two things will not change depending on which charge I brought that day to test this field. So my little test charge feels that sized force. It is this large. So I find that the electric field at that location in space has a size of 2 newtons per coulomb. Its direction is the same as the force on Q0, because that's how I define electric fields, is look at the force on my little test charge and say, all right, that's the direction of the field there. Do you see why if I had brought a negative charge, it would wreak havoc, though? Because now I'm saying all my electric fields are opposite the direction I'd measure with a positive. That's why we got to pick one. That's why I say a test charge will always be a positive charge. Okay, but that's what I find is here, the electric field is 2 newtons per coulomb. And you can actually read that as it is that many newtons of force, 2, per coulomb of charge that you bring and put in that spot. So that helps answer the next question. If I bring a new charge along, this will be my Q new, and I plop it right here. I say, all right, now that I've measured the field, I want to pull out a different charge and say, well, what's the force on it going to be? How would I find the force on it? I did the dirty work in part A. I did the hard step of actually measuring things and calculating. Now I reap the rewards. I say for any charge I've got in my pockets that I want to find the force on, it's super easy. Just take that charge and multiply by my electric field. And I really should have absolute values here because this is just telling me about the size of the force. I have to worry about direction as a separate step if I want to not use that vector equation. But what is the direction of the force on this new charge I brought?
Along the field.
Yes, along the electric field, because I brought a positive charge. It will do the same thing as the test charge did. So this is the force on my new charge in part B. Okay? And now in part C, some other guy, some dummy brings along his negative charge and he says, okay, what happens here? Okay, Sajid, I see a question.
So when we're describing the direction of an electric charge, do we do it relative to the test charge?
Yes, so it is the direction of the force on this new charge. And the reason it's relative to the test charge is because that's what I decided to use to define the direction of my field in the first place. Let me come back up here for a second to say why it's a problem for electric fields, but not for gravity. For gravity, there's a very clear direction for everything, for every pull, because there's only one type of mass. For charge, it's a problem because if I used a negative charge, all of these forces would be opposite. And then I would be compelled to define the field to be in the opposite direction. But it's not because the thing in the middle changed. It's because I changed my measurement device. So I kind of am forced to pick. And my convention from here on, what I say I'm going to choose to define the electric field as, is the force on a positive test charge. I'm not going to use negatives to ever test these things. People can bring in negatives later, like we're doing here in part C, and that's not going to cause issues. It's just when I do this initial measurement, I'm going to make sure I always use a positive charge. So what if someone brings a negative? What do we do?
Same as we did in part B, but the direction will be opposite of the field.
Exactly. So the force is still very easy. Just take the size of the new charge you brought and multiply by the electric field.
And the direction will be the opposite along.
And that is going to be what happens. I bring, or somebody brings their negative charge. This is Q new for part C. And I say, okay, no problem. Here's your force. Here's the size of it. And since you brought a negative charge, I know the force will be opposite the direction I decided the electric field points in. Because when I decided that, I used a positive test charge to decide it. And hopefully what you're seeing is this is a much faster procedure than recalculating the force directly every single time. If you find the field, it's sort of doing half the work for you already, and all you got to worry about is the new charge you brought, not everything else going on around it.
I have a question.
Yeah.
So for part C, would it be negative 48 times 10 to negative 8, or is it?
It is not, because we're separating the size of the force, which is just a number saying how hard is it being pushed or pulled, and then the direction is a separate question. And that's the only reason that the negative is important to know, is direction.
Okay.
Yep.
Thank you.
If I used this version that bakes everything in at once, yes, negatives would pop up, but that's why I don't really like to use it, because I think that actually becomes more confusing.
Okay, I understand it. Thank you.
Okay, so we'll look at a quick application of this. So this is like a really abstracted version of an inkjet printer, but what they do is they have little droplets of ink. They have what's called like an atomizer to turn it into a spray, sort of like what you have from a Febreze can or something like that. And they make these little globs of charged ink droplets. And what they do is have a charge on these plates. And those charges on the plates produce an electric field that these ink droplets then sit in, are then having to experience. They're riding the waves of that electric field. What would the direction of the electric field between the plates be?
Would it be going up?
Well, we can always answer this by asking, what would a test charge do? It's like, what would Jesus do? What would a test charge do if I put it right here? Which way would it go?
Down.
It would go downward. It's repelled from the top plate, attracted towards the bottom. So I, the electric field inspector, pulled out my little test charge, found it went this way, and I declare from here on ever after, the electric field between these plates is downward. The size of the electric field is, again, the size of that force on my test charge divided by how big the test charge was that I used. And now I can answer these questions for any other kind of charge. Say this, I'll actually color it red now. Say this was a little positively charged ink droplet. What's it going to do once it moves between the plates?
Go down as well.
Yes, it will go in the same direction as my test charge I used to measure the field. And so, since it was already moving to the right, it got launched in by this sprayer, this atomizer over here. It's going to go to the right and downward. It's going to be deflected down. If it gets deflected down too hard, it'll run into the plates, but if not, it makes it through to the other side. And I'll tell you what this is on the other side in just a second. Now say I send in a negatively charged droplet. Then what? What's it going to do?
Go up and to the right.
Yeah, it'll be attracted towards the top plate. It'll go opposite the direction that the test charge went. And now what I can do is, if I put more charge on these droplets, they will deflect more. If I put less charge on them, they deflect less. So a small negative charge droplet might end up here. A large negative charge, so it doesn't have to mean a big droplet, just one that carries a lot of negative charge, will end up higher. And then over on this side, a small positive charge will be deflected a bit downward, whereas a large positive charge will be deflected a lot. And so we've come up with a way to control exactly where these droplets land just by controlling how much charge is on them and whether it's positive or negative. So what's this thing over here? It's the paper. That's how you print. You put droplets where you want using these deflecting plates. So the deflection is controlled by the charge of those droplets. There are versions of these printers where actually they change the charge on the plates and it will have the same effect. This way just lets you do it a little bit more rapid fire because you can control per droplet rather than having to switch the charge on the plates rapidly for each droplet.
Oh, I have a question. So, like, if you were to run out of ink, would that mean you have less charge input?
It would carry less, it could hold less on its surface, so that is a possibility, but that is more just because you have less ink to work with. You're not going to see a clear print because of that. You don't run out of charge because it's generated by a voltage that comes from just the power from the wall. If the question is like, why do prints start looking bad after a while, it's not because you run out of charge, it's because you actually run out of ink. So we've kind of looked at electric fields in a general sense. Now we're going to look at a specific thing and what kind of electric field it creates. The specific thing I am now interested in is a big glob of charge, a big point charge. This will be my charge of interest Q. But my procedure to find the field it creates is the same as always. So I want to measure the field it creates, say, right here, a distance of 0.2 meters away. So this is a charge with a value of 15 microcoulombs. How will I determine the electric field at that point? What do I do?
Get the force and then get the electric field after you get the force.
Perfect. So I pull out my little test charge. I put it at this point. So there was nothing there. I'm just going to pull out a test charge and see what happens to it when I place it here. So this is my little 0.8 microcoulomb charge. And what I'll find is, since it's a positive charge, it'll be repelled. So here's the force on my test charge. And I use that to define the direction of my electric field. The direction of the electric field at this location forever after is going to be this way, to the right. The size of it I have to compute. So, to find the electric field at that point, I take my measurement I found for the force on my test charge, and I divide by the size of the charge I brought that day. So again, as a reminder, this thing is created by the big charge, Q, but I can measure it with my test charge. And what's nice for a point charge is I know exactly how to find the force between 2 point charges. How do I do that?
K times absolute value of Q1 times Q2 over R squared.
Yeah, so in this case, my 2 charges are the big charge I'm interested in, and then the little test charge. This will give me the force on my test charge, and then divide by the square of the distance between them. And then, so I get a number that does not depend on what charge I brought to measure this field, I divide out by it. And look, that really does work because Q0 cancels out of the equation. No matter what charge I brought, I could have brought a 0.8, I could have brought a 1.6, I could have brought any value for this little test charge, and it would not matter because what I end up getting does not depend on it. That was the point. It should not depend on my measurement device. It only depends on the big charge. And now I can find a value for it. So it's 8.99 times 10 to the 9th. That's K. Absolute value of the big charge. So 15 microcoulombs, so 10 to the negative 6. And then the distance was 0.2 meters. And we square that distance. I get 3.4 times 10 to the 6 newtons per coulomb, which again you can read as, for each coulomb of charge I put at that location, it will feel a force of 3.4 times 10 to the 6 newtons. So if I put 2 coulombs there, it'll feel 6.8. If I put 3, it'll be whatever that number is, 10.2, I think, times 10 to the 6. All right. Part B. What changes if not my test charge, but now I actually change the big charge? Now it's a negative. What changes about the electric field? Still at the same location.
The direction of the force?
Yeah, so if I put my little test charge at that location now, it's going to be pulled towards my big charge. And so my electric field, which I'm defining based on the direction of this force, is going to point the other way. But that's okay. The thing creating the field, the big charge, actually did change this time. Something legitimately changed, and it's not just I brought a different charge in my pocket that day. The thing that makes the field is a different thing for part B. So it makes sense that the electric field is a little different. What about the size or strength of the electric field, though? Is it different?
No.
No, because the size of the charge did not change. It's just a negative charge now instead of a positive. since the absolute value, the size of the charge, is the same. So this is what I was saying about positive or negative charge matters for direction. It does not matter at all for the size of the field. Right? And this is just a summary. So if I want to know about the electric field at some point in space near a positive charge, I will always find that a little test charge placed there will be pushed away. So the electric field there will be away from the positive charge. And notice I don't need to draw the test charge anymore. It's just a measuring device. It's like if I measured temperature, I can just write 70 degrees right here. I don't need to keep drawing a thermometer. So once I found the electric field, I can throw out the test charge. I don't need it anymore. Meanwhile, for a negative charge, I will always find that a little test charge I pull out is attracted to it, pulled towards it. And so the electric field there is going to be towards it. Once I know that, I can throw away the test charge. I don't need it anymore. I just needed it to find E. E is the important thing. And if I want to find the strength of the electric field, it's just the force on my test charge, which again is not pictured here, but if it were placed at the black dot, it would feel a force of K, Q, Q0 over R squared divided by the size of the charge, the test charge I used to measure this. And so I get KQ over R squared, where R is just how far away is this point that I'm interested in finding the field at. And again, this is the size of the big charge, because it is the thing creating this electric field. And I guess that puts us at time. Are there any questions on that? If not, quick thing to think about then. I kept worrying about the big charge in the electric field it creates. But a test charge is a charged object. Does it create an electric field too? And if so, why didn't I care about it? Ask yourself that. All right. I will see y'all hopefully in person on Friday, though.